So this is Amrita University's homepage for physical sciences. So we scroll down and we go to laser optics virtual lab, because this Michelson's interferometer experiments, um, in actually they are also done with the help of sodium source, but for that thing you don't get a pattern on the screen, you have to observe it through the telescope. But that experiment is really old and laser came much later than that. So nowadays laser is a popular choice for performing Michelson's experiment, because you get to see the pattern on the screen, so it's very easy to analyze. So here there are n number of experiments with the help of laser. You can also, go through the experiments for Brewster's angle, even Newton's ring that we discussed, laser beam divergence. So they are basically, other than optical fiber, the most basic experiment here, which is Michelson's interferometer for wavelength of laser beam. So as you know, it's an interferometer which make use of the property of interference of light for measuring some quantities. So here that quantity under measurement is wavelength of laser beam. So here you are given aim. The aim of this experiment is to determine the wavelength of laser using Michelson interferometer. The apparatus required is laser light source, Michelson interferometer kit, optical bench. Here they will be using, the 2D optical bench. The optical bench comes in many forms. The one which you have seen maybe in your, school time is the long bench where you do lens experiment and all. But here it's a little, advanced version of that, which is a two-dimensional optical bench. And you have a meter scale. M2 and M1 prime, both are mirrors, and they are making parallel virtual air film in between one of the mirror and image of the another. So when you see observe from the here, you have one virtual source which is creating another two sources, S1 and S2. Hence, the net optical part difference between S1 and S2 is 2d cos of theta. So because of that phase reversal which is happening at beam splitter, our delta is 2d cos theta equal to lambda by 2. So if this is equal to m lambda, then you get a constructive interference. So in order to accommodate this lambda by 2, we simply say that 2d cos theta equal to m lambda is the condition for destructive interference, and the other way around is the condition for constructive interference. So this lambda by 2, I simply take this side and it will become m minus, 1 by 2, like that. So it becomes easy that way. Okay. Now, if we are looking at the central fringe, we don't need to take into account this theta, because theta will become 0. So cos 0 is 1. So our equation now modifies to simply 2d equal to m lambda, n lambda, where n is the order of the fringe. Here, cos of theta we have removed because theta is 0 and cos 0 is 1. Also, this m is replaced with n, because now we are saying that we are actually going to count the number of fringes which are appearing or disappearing. So here, one sec, yeah, here our m2 is the movable mirror. So let's say we are shifting m2 in such a way that your d is changing. So the change with, let's say, d is by some d1 and d2. Let me just write here. Let's say I'm having small d1, okay, and or what we used in theory was x1. So x1 is the distance of mirror m1 from the beam splitter, and x2 is the distance from m2 for the beam splitter. So basically here to here and here to here. Now for the starting point, when you have x1 equals x2, can you tell me what will happen at the center? If x1 equals x2, we are saying that our small d, which is equal to x1 minus x2. So given x1 equals to x2, d will be 0. If d will be 0, center will be bright or dark? Dark, right? Because we are considering that phase reversal over here. Now, let's say now my x1 and x2 are not equal. Okay. So for all unequal x1 and x2, now D will have a finite value x1 minus x2. So let's say for now, I move my mirror M2 by some extra distance delta. Okay. Then can we say that my modified D will be equal to, since we are going to take the mod, okay, so this sign is really irrelevant what you are getting. So I can write x1 minus, I increased the distance of M2 by delta. So let's say x2 plus, and I'm giving it here, delta, bracket close. And then here I have mod again. In this situation, what will be your net D? So let's say this was my one condition. So my first condition was D, and let me call my new condition as D prime. Are you following? My first situation without moving anything was like that. For x1 not equal to x2, D was given by x1 minus x2. Now we increased the distance of M2 by delta. So now my new D prime would be mod of x1 minus x2 plus delta. Let me put mod here also, so in order to avoid any confusion. So now can I say that my net change in D is delta? So one situation to another, we changed the distance by delta. Hence, now for writing equation, what I will write? Now this is D, so my optical path difference is twice of that. So here now my new equation will become twice of this delta if it is equal to, let's say n times lambda. So if this is n times lambda, here this n is also the difference between the two, because this D will also satisfy equation. So this, for this D I can write, let me use another color. I'm just defining equation now, okay? So for this D, I can write 2D equal to some n1 lambda and for D prime we can say 2D prime equal to n2 and again lambda. Okay, so your delta is basically the difference of the two. So if I want to calculate the optical path difference, so what you will do, subtract the two equation. So you will get twice of D prime minus D, which is nothing but this delta. So we get the equation 2 delta equal to n lambda, where our capital N is the difference between the two. So capital N is N2 minus N1. Because we have discussed that the order at the center is highest, and we can't know it until unless we have all the values set out for us. So rather it is easier to calculate the difference. With that, we can give total disregard to what was the order at the center. What we are interested in, how many fringes appeared or disappeared during the process. So if we are increasing the distance, fringes will appear. If we are decreasing the distance, fringes will disappear. Here, whether the center is dark, then you can measure consecutive dark fringes. If the center is bright, you can measure consecutive bright fringes. That is also same. Hence, we get this equation, so that our 2 capital delta, which is the distance by which our mirror is moved, Which mirror is moved? Only the movable mirror. So if my movable mirror is moved by capital delta, capital N number of fringes appear or disappear. So if I know both the quantities, I can easily calculate lambda. Okay. Now let us go to our main working tab. So procedure I have already told you. Please go through it. It's the same. So I'm not showing you. Go to the simulator. So this is our Michelson's interferometers virtual setup. It's a very, I can say exact replica of Michelson's, leaving one or two arrangements. So as you can see here, you can power on first. You are given a choice of lasers: krypton, helium neon, argon, ruby. We will stick with helium neon laser. Power it on. You can also see the ray diagram here. So this is laser. This is our beam splitter. So you can see that one of the beam is going towards mirror M1, and because it's a beam splitter, it will split it into two halves. One half is going towards this side because it is kept at 45 degree. The other half is going straight, and this can be moved, which we also are at liberty to move it. So this is our movable mirror. You can also see the adjustment of the screws, which is not available in this setup, but in real Michelson, these are the screws with which you actually tilt the mirrors and get the cross. So here our both mirrors are exactly perpendicular. Hence, this mirror will get image of this mirror behind it. So we will get a virtual air film. And since the ray is going here, coming back to the screen, and once coming here, it comes back, reflect from the beam splitter, because of which we get that phase reversal extra, part difference of lambda by 2 or phase difference of pi. It goes here, and these two rays are interfering to give you the circular fringes. Okay. So now we have to adjust the mirror. So this is a fine adjustment to get a very clear pattern. So it's similar to that Cauchy's constant. So when you take it even farther I go, it will become blur. So we want to adjust the mirror so that contrast of my fringe is very nice. So this I can say is a good contrast. Now next you have to adjust the micrometer. Before doing any micrometer arrangement, first let us calculate the least count of this micrometer. This is a screw gauge. So let me just open it a bit. So you can see the number of divisions on this circular scale is 50. You can see 0, 45, so 50. And this is 0 and this is 10 mm. So the least count of main scale division is how much? What is the minimum reading that you can read through this? See, you can see it is 0 to 5. So how many breaks are there in between? One, but you also see one scale below, which this is exactly in between the two. So the least count for main scale here is, so if you have 10 divisions here, so this will become 0.5. So your least count is 0.5 mm. So if only 10 divisions were here in between 0 to 10, you will take 0.1. And because it is again divided by 2, that makes it 0.5. So what is our equation for calculation of least count? LC is equal to, so 1 MSD, that is 1 main scale division, divided by number of divisions on circular scale. So least count equals 1 MSD divided by number of divisions on, here it will be circular scale or CS only. Okay. So what will be our LC here? Our 1 main scale reading is how much we said? 0.5 mm divided by what is the total number of divisions? 50, right? So 0.5 divided by 50. So how much will be our least count? LC would be 10 to the power minus 5 Let us keep it in mm only. Can I say minus 2 meter mm? So minus 2, or it is easier to write it as 0 0.01. 0.01 mm. Okay. So whenever you calculate the total reading, what is total reading? Total reading equals, I'm just repeating it. Otherwise, these are all the things which you all know. So MSR plus CSR into least count. Okay. So here your main scale reading will also come in mm. That's why it's better to keep the least count in mm. So plus circular scale reading multiplied to the least count. Now here it's very important to see that this is our normal screw gauge. But you know the real Michelson interferometer, that so there it is mounted with the double gear arrangement kind of screw. So there is one more uh, micrometer attached to this one. So our least count, if I am not mistaken, goes like we can measure up to with the least count of 10 micrometers. It's very fine. This is quite coarse, but nevertheless, it's good to see this experiment in, almost close to the real apparatus. So I'm happy with this. Yeah. So now let us start our experiment. So this is your observation table. You have to count the number of fringes. You can make your own table. It's a very, easy table. So basically what you will write is serial number, write your main scale reading, circular scale reading, or you can directly take the total reading, and that will give you the total reading is the distance through which it is moved. So if let's say your first distance is different and second distance is different, then you can also start like, first distance minus second distance will give you this difference. So let us you started with 0 and then you reached some distance. Let me say you started when with our first distance was 0. Okay. Then your difference is also 0. This is my first reading. For second reading, you have some distance d1. Then your difference will become d1. Then, and this, let's say you are doing for, but minimum number of fringes that you should count is 20. Minimum, don't go below than this. If you go lower number than this, then the chances, I don't know what is, the background code in the simulator, but generally more is the number of fringes, better is the accuracy of our measurement. So if my next distance is d2, the new difference would be d2 minus d1. So do for such 5 distances. In one shot, you keep on going ahead and ahead. Next, I take d3. So my next, so this difference will be d3 minus d2. Such 5 readings you take. So barring this, because this is 0. So this will be your first reading. D2 will be second reading, third, and so on till at least 5 you take. More the merrier, your choice. Okay, and then take the mean of that delta D and substitute that for the calculation of wavelength. Now let us bring it back to 0. So this is 0 reading. Now we are going to increase the distance. So if you see what is happening here when I'm changing, now I'm controlling it with the help of a, keyboard forward backward arrow. So you have right arrow, left arrow. So that gives you a better control instead of, scrolling it. Those who are using mobile, I can't help it. But those who are using laptop, I advise that use this only. So whenever you click it and it is highlighted, then you can control it with the help of laptop's keyboard. So here we are starting from 0, but it is not required that every time you have to start from 0. Since we are starting from 0, our D1 is already 0. So whatever we read will give us that 2 delta. Okay, where was that? 1 minute. So here our first situation is starting from 0, but you can start from any random situation. And now we are going to count the number of fringes that are appearing or disappearing. So now let us go back to our 0 reading. What happened? Now this is 0. Now tell me, when I'm increasing the distance, the fringes are appearing or disappearing, you tell me. Appearing or disappearing? Yes. Can you see them going out, appearing? And see, now I'm going other way around. Now they're collapsing at the center. Can you see the pattern shrinking? This, this is a simulation. It's not a real thing. Otherwise, when you are set such that my micrometer is in 0 position, and if my D1 equals 0, you should get a completely dark pattern, because when your X1 equals X2, your D is 0 and you get a dark screen. But here your X1 is X2 looks like already not equal. So let us start counting. So now I'm changing the distance. Let us count. 1 minute, let it go back to 0. Yeah. So my center is dark. I'm going to count the appearance of dark fringes. So let's say we do 20. Okay. Look closely at the center. Let me make it even bigger. So in my laptop, it is happening as if once I'm changing, my center is going bright to dark. So, previously what it was, we started with a very big dark. In one click, I'm reaching here. In the second click, it is again becoming dark. So in 2 clicks, my one fringe order is changing. Okay. So this will count as 1. Okay. 2. This has only got bigger. We have not got new black fringe. Okay. So let us start again. I'm starting. You also count with me. So I can see dark center. I can count this as only 1. Okay. This is the same as gone bigger. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay. Now let us look at our micrometer reading. What happened? Wait a minute. I'm not able to zoom out now. Okay. So now we have moved, and now let us read this scale. How many fringe appearance we calculated or counted? 20, right? What is my main scale reading here? 0. And my circular scale has only crossed 5. It has not crossed 6. It has just crossed 5. So what is my total reading going to be? So our total reading will be, main scale reading is 0 plus 5. So our reading would be 0.05 mm. This, what we have got now, this is the distance by which we have moved the mirror. So this is our change in D. We are calculating twice of that. So if we substitute, we will get, let us put it in the equation and see what we are getting. So we will have 2 into twice of this 0.05 mm equal to how many number of fringes we counted? 20. So 20 into lambda, that is our unknown quantity. And convert your answer in nanometers. 0.005 mm. Convert it to nanometer. So it will become 5 into 10 to the power minus 6. So it will become 5000 nanometer. So the answer is actually close to 500 nanometer. But it is the limitation of this simulator that it is giving 10 times, more value. Do it the way it is happening, because this is a good way to see how Michelson's work. But there is problem with the simulator. So, just now what we did, if I click on show result, see what is happening. Here also you can do, just click on show result and look at this, what it is giving me. It is giving me answer as 543 nanometer, and our answer is 10 times more. Okay, so whatever you are getting, you report, and also write a note in the bottom that you have counted it, but the issue is with the simulator. What I guess is happening is, you know uh, in terms of Michelson's, when we are changing it by 0.05 mm, it's a very big distance. Many number of fringes can come up in that much width of a air film. I mean, even if it is giving us a wrong answer, the idea is to see how Michelson works, and that is being fulfilled. So we will stick with it, but be mindful of this wrong answer. Now, with the given data, let us quickly cross check why we are sure that the answer we are getting is really wrong. In the simulation, we got for 20 change of order at the center D as 0.05 millimeters. And we know the equation for change of order in Michelson at the center is given by 2D equal to n lambda, where D is the separation between the mirrors, which we got as 0.05 millimeters, for order change in the center, which was 20. But there is a checkbox in the simulator. If you click that, you get the answer for lambda as 5430 angstrom, or I can write 543 nanometers. Now let us try and substitute the given value of lambda and order n and quickly cross check what should be the D if lambda is 543 nanometer. Because in our answer, we are getting answer as 10 times more. That is, answer is coming out to be of the order of 5000 nanometer, which is beyond the optical range. So let us substitute. Now I want to calculate D, which will be n lambda by 2. N is 20. Lambda is 543 nanometer. So I am doing the calculation like, in order to get this lambda, how much should be D? This will give me the answer as 5.43 multiplied to minus 6 meter, or 0.00543 millimeter. This is expected value of D. That means for 0.005 millimeter separation of the mirror, n should change by the order of 20. Whereas in the simulator, when we are changing n by the order of 20, our D is only changing by 0.005. So if you recollect, there MSR was 0, CSR was 5, and least count was 0.01 nm. Hence, the total reading was MSR plus CSR multiplied to the least count, which comes out to be 0.05 mm. So now if you compare the two, this is 10 times bigger than what we should get. And that is why the answer is coming 10 times more which is taking the wavelength beyond the visible range. Anyway, this is a good way to see how Michelson works. So that's why even if your answer is coming wrong, the procedure is all right. The problem is with the simulator only. Thank you.